Differential equations, we're now in chapter 4. And just a real quick reminder about what we've been studying so far. If the right-hand side of a differential equation is equal to 0, we will call that a homogeneous differential equation. This chapter, we're going to go to higher orders, derivatives of higher orders, of course, like a second derivative, third derivative, and so forth in our differential equation. Likewise, if our right-hand side f of x is not equal to 0, we have a non-homogeneous higher order differential equation. And take a look at this superposition principle. If you have y1, y2, all the way up to y sub n solutions to an nth order homogeneous differential equation, and we're saying if these are linearly independent. What does it mean to be linearly independent? Well, it means that if you were to combine them, put some constants out in front and add them together, there would be no way that you could ever get 0. So what we're going to see is that you won't be able to have multiples of some of them to get others, or even the opposite of others. So, but let's just say that we have n linearly independent solutions. You combine them with constants, you can't get 0. Then, right here, this combination, adding all of these separate constants, is also a solution. C1y1 plus C2y2 and so forth. Suppose that we had, for a fourth order differential equation, let's just say that these are the 4 solutions that we found. These are not linearly independent. They're not linearly independent because we can add or subtract multiples of some of them to get others of them. Or, like we just said, some combination of them would equal 0. So take a look at this. Cosine squared and sine squared, we could put 1s out in front. We happen to know that that would add up to a 1, right? And if we put 1s out in front of secant squared, or choose a negative 1 out in front of secant squared, look at this. 1 plus tangent squared actually equals secant squared, a very famous identity. This would actually add up then to a 0. Another way we could look at it is if we'd combine those 3, cosine squared, sine squared, and tangent squared, and then if we put a negative constant out in front, we could also find a way to get some form of secant squared. So regardless of how you look at it, as if you're saying that multiples could arrive at one of these answers, or if you combine them to get 0, the bottom line is we don't like to see this happen. We'd like to get linearly independent. So suppose we solve and we get sine e to the 3x, e to the 4x, and x plus 3. These certainly appear to be linearly independent. We don't seem to know identities that would link 2 or 3 of these to get another, or adding some constants of all of these wouldn't add up to 0 if we just would, try to immediately think of a way to do that. How do we know for sure, though, that we couldn't put constants in front and get 0? Well, today we're learning about something called the Wronskian. And the Wronskian is a wonderful tool that we can use to check for linear independence. Let's just say you found n solutions. You've got n solutions, and then you take multiple derivatives. This would be for an nth order differential equation. So let's say we came up with n solutions. Take a look at your first row. It's just the solutions. y1, y2, y3, all the way up to y sub n. Second row, take your first derivative of all of those solutions. Next row, take your second derivative, and continue to go on until you get to the bottom row you'd be taking the n minus 1 derivative. Guys, if you work this determinant out by hand or on the calculator, as long as that Wronskian determinant is not equal to 0, then those solutions are linearly independent. It's a wonderful quick check for us to say, you know what, we do have linearly independent solutions. So that's really what we're seeing right here. Let's jump in and see where we're going with this. Let's just take a look at this differential equation. Y double prime minus 9y equals 0 says that we have solutions of e to the 3x and e to the negative 3x. First, verify that they're solutions, and then see if they are linearly independent. Well, let's just take a look and see where we're going with this. We're saying, hey, y equals e to the 3x. Take your first derivative, you'll get 3 e to the 3x. You can take a second derivative if you'd like, and that would bring down another 3 via the chain rule. And let's check this. Let's just see if this is in fact going to work. We're going to have 9 e to the 3x right here minus 9 times our y, which is e to the 3x. Hey, this checks. It's good. We do in fact have a solution. Let's check y equals e to the negative 3x. Well, our first derivative is negative 3 e to the negative 3x. Second derivative, bring down another negative 3, we'll have a 9 e to the negative 3x. And then what? Well, we go ahead and we're just saying, is this really a solution? Well, we're going to verify that it is. You can see that this left-hand side does in fact cancel out to 0. So both of these work. The question is, are they linearly independent? So we've got two solutions. Let's check the Wronskian. We have two solutions. We'll have e to the 3x, e to the negative 3x. And the question is then, take your derivative. We'll have a 3e to the 3x. We already did this. Here we'd get negative 3e to the negative 3x. With a two-solution situation, you'll have a 2 by 2 determinant. And for a 2 by 2 determinant, remember we can cross multiply. We'd get a negative 3, and here's e to the 3x times e to the negative 3x. Well, guys, you're just going to add those powers together. Then we subtract, remember, and then we're going to multiply over here. We'd have a 3e, and we're going to add these just as well. And this is really going to be negative 3e to the 0 minus 3e to the 0. E to the 0 is just a 1, however, and we're going to get negative 6. And negative 6 is not equal to 0. So what do we know? Therefore, e to the 3x and e to the negative 3x are linearly independent. More to the point, we can solve for a general solution right now. Because these are linearly independent, we're going to say, you know what? This is the most general solution that we can come up with because we have linear independence. We can superimpose these two answers together. Not only are they answers, but any combination of them with these constants would also be a solution. That's really taking it a step further. Let's very quickly take a look at this last one. And they're saying, hey, we have solutions. They're telling us e to the x, e to the 2x, e to the 3x. They're all solutions. But determine if they are linearly independent solutions. Look at this, a third order differential equation right here. Well, I'll tell you what, we've got e to the x. Because we have a 3, we're going to make a 3 by 3 Wronskian. y prime is e to the x. Y double prime is going to be e to the x. That works out rather nicely, doesn't it? Here's our other solution, e to the 2x. The derivative would be chain rule, e to the 2x, 2 times e to the 2x. Have another chain rule, multiply by another 2. And then finally we'll have e to the 3x. Take a derivative, bring down another 3. Of course, e to anything right there has a derivative of that. We're just using the chain rule. We have 9 e to the 3x. And let's check our Wronskian. So here's our first solution. Its derivative, its next derivative. Here's our e to the 2x. Here's the derivative of e to the 2x and the second derivative of that. Here's our e to the 3x. Take its derivative. Take one more derivative. And the big question, of course, is what is this Wronskian? Well, I'll tell you what, we've learned how to do this by hand, and certainly we may. And, we can talk about the basket weaving method and so forth. But I do want to just point out, and we've talked about this before too, on the TI-89. For the sake of time on this video, time is getting rather short. I do want to, instead of typing it in, which would take a little bit of time to load up the emulator and so forth, go to catalog, find determinant, DET, parentheses, then hit the square bracket, and you'd go A, B, C, then you have to hit the semicolon. A, B, C would be row 1. Then you'd type in D, comma, E, comma, F, hit a semicolon. That would be row 2. And finally, you'd have your last row, which would be G, H, I. And that's row 3. And, the cool thing is then you've got to close your bracket and then close your parentheses. It gets very particular if you don't close that off. You get an error message. I'll leave it to you to type this in. It just takes a little bit of time. I've already done it. You should get 2e to the 6x. By the way, you could do that by hand also. That's not 0. Therefore, the solutions are linearly independent. More to the point, we could talk about a general solution here. We saw that we had 3 different answers, but look at this. We can combine these with these constants and also have a solution. For example, if I chose C1, C2, and C3 to be 1, e to the x plus e to the 2x plus e to the 3x would also solve this differential equation. Pretty cool. Now, this is 4 homogeneous differential equations. What if we had a non-homogeneous? Well, we're going to get into that in due time. What you're going to see is you would have the general homogeneous solution. We're still going to solve that even if the right side isn't 0. We pretend just for a moment that it is, and we're going to get an answer that we just came up with. And then we'll solve for a particular solution where the right-hand side is that something different, and you add it together. We'll talk a lot more about that down the road. You might say we're planting seeds so that you can see that in the very near future.